This is part 3 of the series Right Triangles and Trigonometry, and we're continuing on with a discussion of special right triangles. And the special right triangle we're talking about here is a 30, 60, 90 right triangle. This is the second of the two. The first one was the 45, 45, 90. Here we have, in a 30, 60, 90 right triangle, the hypotenuse is twice as long as the shortest side. So here's the shortest side, which is opposite the smallest angle, the 30-degree angle, and the hypotenuse is twice that side. And the longest leg, which is opposite the 60-degree angle, is going to be the shorter leg multiplied by the square root of 3. So again, in a 30, 60, 90 right triangle, the hypotenuse is twice the shorter leg, and the longer leg is the shorter leg times the square root of 3. So each one of the sides is given in terms of the shortest leg. And that's going to be a critical factor when we solve for 30, 60, 90 right triangles. Now, the proof of this theorem is a little less straightforward, but it's still an important thing to go through. So let's take a look at that. For this proof, I've drawn an equilateral triangle. You can see that each side has a length c. And I've drawn an altitude from a vertex perpendicular to one of the sides. In a previous unit, we learned that an altitude in an equilateral triangle is going to be a perpendicular bisector of both the side that it's perpendicular to and the vertex angle. So since this is an equilateral triangle, it's also equiangular. So each one of these angles is 60 degrees, and since this altitude bisects this angle is 30 degrees. So here we have a 30, 60, 90 right triangle. And I've labeled this side A and this side B, so that here the side length of our original equilateral triangle is the hypotenuse of our 30, 60, 90 triangle, and that's labeled C. So to do this proof, we're going to use the Pythagorean theorem, and that says that the sum of the squares of the legs equals the square of the hypotenuse. So we're going to say a squared plus b squared equals c squared. Now we know that since side C has been bisected by this value, by this altitude, we know that A is 1/2 of C. So if A is 1/2 C, then multiplying by 2, 2A equals C. And there we have our first property, where we say the hypotenuse, C here, is twice the shorter side. So twice the shortest leg. That's this piece. Now that's all we have to do is prove that the longest leg is the shorter leg multiplied by the square root of 3. So since we need to relate this shorter leg and the longer leg, I'm going to replace this C value with what we just determined it was in relation to the shortest leg. So C is equal to 2A, so I'm going to make that substitution here. So we know that A squared plus B squared equals 2A, replaces C, squared. Now, working this out, we have A squared plus B squared equals 2 squared is 4, and A squared. Now we're solving for B, so we're going to subtract A squared. So we have B squared equals 4A squared minus A squared is 3A squared. And then we're going to take the square root of both sides. So B equals the square root of 3A squared. And this simplifies. B equals the square root of A squared is simply A, and the square root of 3 is left inside. So B equals A times the square root of 3. And there we have it. B, the longest leg, is equal to the shortest leg, A, times the square root of 3. And there's your proof. So now let's move on to some examples. In our first example, we notice that we have a triangle and it only has one side given. Now clearly we can't use the Pythagorean theorem because we only have one side. So this is a requirement. We're going to need to use these special right triangle relationships. Now there's a simple 4-step process that if you apply this to each one of your problems, these problems become very straightforward. So, step 1. ID your triangle. So we look at this and we try to determine, what is this? Is this a 45-45-90 or 30-60-90? Here we can see that the two legs are equal. That means this is an isosceles right triangle, therefore it has to be a 45-45 right triangle. All right, step 2. Label your sides. This is the critical step, labeling the sides. And I would strongly recommend that you do it in just this way. So this side equals A equals A equals A square roots of 2. You put in your relationships just as we showed when we did the 45-45 right triangle. Now, the third step, solve for A. We're going to use this equation to solve for A because we don't have anything else to use. So 12 equals A square roots of 2. We're going to divide both sides by the square root of 2. The square root of 2 divided by the square root of 2 is 1. Now we can't leave this the way it is. At this level, it's not acceptable. It's not considered simplified to have a radical in the denominator. And when you get to calculus, it's not really going to matter much. But at this level, we're going to need to do something called rationalizing the denominator. That means getting rid of the radical down in the denominator. The way we do that is by multiplying the denominator by itself. So we're going to multiply by the square root of 2. If I do that to the denominator, I had better do it to the numerator, because square root of 2 over the square root of 2 is just 1, and multiplying any value by 1 doesn't change the value. It just changes the way it looks, and that's our goal, is to change the way this looks so that the radical is no longer in the denominator. Multiplying this through, 12 times the square root of 2 is 12 square roots of 2. The square root of 2 times the square root of 2 is simply 2. So you know that the square root of 2 times the square root of 2 is the same as the square root of 2 times 2. And you remember when we did our simplifying of radicals, any pair of numbers inside the radical comes outside the radical as one of those numbers, 2. Square root of 2 times 2 is square root of 4. Square root of 4 is 2. So either way you look at it, any pair comes out as one of those numbers. 12 divided by 2 is 6 square roots of 2 equals A. Now that we have our A, the fourth step is solve for your sides. And in this case, A is the answer. So we just plug in 6 square roots of 2 and 6 square roots of 2. And we're done. So let's move on to another example. In this example, again, we have two equal sides, x and x. So this is, again, a 45-45-90 right triangle. And we have the hypotenuse is 2 square roots of 6. So our first step is to classify. We've done that. It's a 45-45-90. Second step, label your sides. So let's go ahead and label our sides. This is A. this is a, and this is a square roots of 2. Now we have to solve for a. So we're going to solve for a using this equation here. So we're going to divide both sides by the square root of 2. These cancel out. And we have 2 square roots of 6 over the square root of 2. Now in this case, it's not really going to be necessary to rationalize. We could rationalize the denominator. If we rationalize the denominator, we would have 2 square roots of 6 over the square root of 2, and we'd have to multiply the numerator and denominator by the square root of 2. And this gives us 2 square roots of 2 times the square root of 6 over square root of 2 times square root of 2 is just 2. These 2's cancel out, and we have the square root of 2 times the square root of 6. And a basic principle of radicals is that a product of radicals is the radical of the products, which means it's the square root of 12. Now this we would have to simplify, and so to simplify that, the square root of 12, 2 is the first prime number, goes into 12 6 times, 2 goes in 3 times. So we have this pair here. So that pair comes out as one of those numbers, 2 square roots of 3. Now that was how we did it if we rationalized the denominator. But if you notice over here, we can just combine the radicals without rationalization. Rewriting this, it's 2 square roots of 6 over the square root of 2. Just as the product of radicals equals the radical of products, you can say over here that the quotient of radicals is the radical of the quotients. So 2 over 6 divided by 2. So this 2 times square root of 6 divided by the square root of 2 translates to the square root of 6 divided by 2, which is just 2 square roots of 3. So you can see that if you apply your radical rules here, it makes it a little easier. But you can still do it by the standard rationalization. It just takes a little bit more energy. Obviously, this is the preferred approach, unless you forget your radical rules. So let's go ahead and move on to another example.